Okay, welcome to example 1 and 7.2 from Math30-1. This is where we actually start to do some of these transformations. This question right off the bat tells us to consider the base function y equals 3 to the x. And the reason for that is that that is the base of both of these exponential functions that we're going to look at. So really important that in this question, y equals 4 to the x or 6 to the x or any other number than 3 isn't important and it doesn't matter. So what we're going to do is we are going to work through kind of a table of values. And really importantly, they give us 5 points on y equals 3 to the x. And we're going to talk about how are we changing those points. And then basically we're going to change them and draw a graph. So right off the bat, if we did compare this to using our transformations, we would see, hopefully, that for this particular question, the a parameter is 2, the h parameter is 4, the b parameter is 1, and the k parameter is 0. Now, both of these have no effect. But it is important that when b is 1, it doesn't affect the graph, and when k is 0, it doesn't affect the graph. That's an important distinction. Well, if a is equal to 2, we have a vertical stretch by 2. If h is equal to 4, we have a horizontal translation 4 to the right. But as you know, what I prefer is saying that any point on y equals 3 to the x, x comma y, will turn into x plus 4 comma 2y. And what they do in the notes here, and I don't mind it, we've seen this before, is that they do it piece by piece. From the first column to the second column is just the vertical stretch by 2, and then the second column to the third column is going to be our horizontal translation 4 to the right. And there's nothing wrong with doing that. If nothing else, it re-emphasizes that you have to make sure that you do stretches and reflections before translations. Now, there aren't any reflections, but you still have to do the stretch before the translation. So what we can see happening in this table is there's nothing really complex, I would argue, happening between the first and the second column. We are just multiplying those y values by 2. So 1/3 times 2 is 2/3, 1 times 2 is 2, and so on. For the third column, though, I am going to take these points that I kind of pointed at in red, and I'm going to add 4 to all the x's. And that's it. Now, I really do like the idea that you could go from the first column to the third column, just by following our mapping. This third column is that x comma y turns into x plus 4 comma 2y. And if I use that last point, that means that 3 comma 27 would turn into 3 plus 4 comma 2 times 27, which I hope we all agree is 7 comma 54. So the mapping gives us kind of a nice, I don't know if a shortcut is the right word, but it allows us to do several transformations all at once, which I think is a pretty big advantage. Now, in order to sketch the graph of the base function, we're going to take the 5 points we just generated and put them on a Cartesian plane. And what that looks like is this graph right here. Now you have a little grid there. Please draw that graph out. Certainly pause the video, whatever you need to do. And then what we're going to talk about after that is the domain, range, our horizontal asymptote, and then any intercepts that we might find. All right, now it does ask us to talk about the effect of the domain on the domain range equation, the asymptote, and so on. If I move the graph forward to the right, which is what happened to go from the blue to the red, because the domain of the blue graph is all real numbers, it is still all real numbers. And I'm just going to put no change there. Now, similar to that, because the range was y was greater than 0, multiplying that by 2, I still get that y is greater than 0 and y is an element to the real. And oddly enough, there is no change there as well. The kind of general rule of thumb is that when x is an element to the real, any horizontal transformation isn't going to change that. Now y wasn't an element to the real, but the horizontal asymptote didn't move, so the range of my graph didn't move as well. Now be careful, the asymptote is not the only thing that'll change the range. What if I did a reflection across the x-axis? That would change the range as well, and we'll see that in the second example. The horizontal asymptote is still at y equals 0, and our intercepts. We're going to talk about x-intercepts. Remember that x-intercepts are when y is equal to 0, but y can't be 0. So there's no x-intercept. For the y-intercept, we know that x is equal to 0, and I really do want you to understand that this can always be done by putting x equals 0 into our equation. So I get that y is equal to 2 times 3 to the power of 0 minus 4. That means that y is equal to 2 times 3 to the power of negative 4. and that's a pretty ugly number, but it means that y is equal to 2 over 3 to the power of 4, or y is equal to 2 over 81. Now that is a point, so the coordinate 0, 2/81 is the y-intercept of that function. Now that's a pretty ugly one. Remember that you can use math_frac on your calculator to go from whatever ugly decimal that is, because it is definitely an ugly decimal, to the fraction itself. And that's that difference between approximate form and exact form. Okay, we're going to do the same thing for the next example. Talking about the parameters is a really nice way of summarizing what we've done already. And I'm just going to maybe put on the previous page here, we'll talk about the effects of each parameter. So I'm going to write y is equal to -1/2 times 3 to the power of 1/5 times x minus 5. Be careful reading this. That -5 is a different font. Sorry, this -5 is a different font than the 1/5 x. So it is a k value, not an h value. Be prepared to have to factor that b out, just like you have in previous lessons. So identifying the parameters, a is -1/2. B is 1/5, H is 0, and K is -5. Now, if A is equal to -1/2, we have a vertical stretch by 1/2, and we reflect over the x-axis. So we do start to see that reflection happening in this question. If B is equal to 1/5, we have a horizontal stretch by, and I'm going to write it as 1 over 1/5, but 1 over 1/5 is just 5. So all of my x values will get multiplied by 5. Last one there, k is equal to -5, means we have a vertical translation 5 down. And all of this can be summarized with x comma y on the untransformed function turning into 5x comma -1/2 y minus 5. Big fan of that mapping. It allows us to go from any point to the final transformed point relatively quickly. And the notes doesn't do that. I know they break it apart via the table. There's no real reason that you need to do that. It is a nice way to talk about it because then we can see the effect of each parameter as we go, but you can always use that mapping to go from start to finish quicker for sure. All right, and that's what they do here. They show just the horizontal stretch by 5 first, noticing that all that's happening is those x coordinates are being multiplied by 5. The next column, what they're going to do is they're going to take all the y values and multiply them by -1/2. Very, very importantly, this has changed the direction of the exponential function. Instead of that function looking like this, after this column, we know that it'll look something a little more gradual, but also in the other direction. And we'll see that on our graph as well. Last part of this table is they shift it 5 down. Now, shifting it 5 down is a little bit tricky because I have to take -1/6 and subtract 5. Well, that can be written as -1/6 minus 5 can be multiplied by 6 over 6 to make it -30 over 6. And that's where that -31/6 comes from. I think it's a little bit easier to see in the other points. If -1/2 minus 5 is -11 over 2. Because -5 is -10 over 2. Nothing wrong with, maybe plugging -1/2 minus 5 into your calculator, as long as you're doing math_frac after that. We do want to use or exploit those fractions as much as possible because exact form does have value and we have to get used to using it for sure. Okay, similar to the last one, I would like to show you what the graph looks like. And we see this. Now, importantly, it is dramatically different from the previous graph, right? It's opening in a different direction. It has a different horizontal asymptote. And the reality is the more transformations you do, the more changes you are going to see into that function. So we're going to talk about domain. You got to love when an x is element to the real because it is very difficult to change that. X is still an element to the real. There's no change on my red graph. Maybe this blue color was a bad choice. I'll just circle that in red. That's about the red function. For the range, again, very, very dramatically different. It is this point and everything below it. And I shouldn't say that point. It's that y value and everything below it. Now, similar to that last question, it's the idea that the exponential piece of the equation, and maybe I'll write it up here. So y equals -1/2 times 3 to the power of 1/5 x minus 5. This piece right here cannot equal 0, which means the value of the function is never -5. So we would have to say that y is less than -5 and y is an element to the real. And the reason for that is we had a reflection. I'll just put reflected over x-axis. And then it's also been vertically translated 5 down. That's why our range has changed so dramatically. All right, the other concepts they want us to talk about are the equation of the horizontal asymptote. So my horizontal asymptote is now at y equals -5. I'd like to point out that that is y equals k, right? We identified that k was -5 in the previous page. And then the last part they want is the intercepts. I'm not going to solve it again. We know that there's no x-intercept. I hope it's pretty clear from the graph that if y is always less than -5, then it's never 0. The y-intercept, I want to do that kind of my standard way. I'm just going to make x equal to 0. So y is equal to -1/2 times 3 to the power of 1/5 times 0 minus 5. That means that y is equal to -1/2. Anything to the power of 0 is 1 minus 5. So I get that y is equal to -1/2 minus 5, which is -1/2 minus 10/2, which is -11/2. And I'd like to point out that we have that on our curve, right? That was maybe not coincidental, but just kind of lucky that one of our transformed points ended up being the y-intercept. And that's always a nice thing when you're drawing that table of values. I would highly recommend that if you're struggling with these, draw the table of values out. That will be a great way, or if nothing else, make your calculator generate the table of values, although your calculator will give you all those ugly decimals, unfortunately.